Okay, we're going to go ahead and get started. I think some people will filter in later on after they return from lunch. So this is the GaN Goes Global panel session. We've had this every year at EDI CON. The session's been tracking China and their progress in the different commercialization and maturity of GaN products. GaN, which initially developed for power amplifier technology for defense applications, has proven its competitiveness in the wireless infrastructure power amplifier market. And now we're aiming for RF energy, some other bigger markets. And it's even spawned off in millimeter wave frequencies, also been used in switching and mixing applications in LNA. So it's finding its wider and wider use every year. So we have distinguished panelists here from some of the expert companies that are producing GaN today. So I think I'll let each panelist just introduce yourselves and maybe talk just a short little bit about what your company offers that's unique in the GaN market. Go ahead, Mike.
Thanks, Pat. So I'm here representing MACOM, and I think a lot of people know, A lot of people know that we are GaN and silicon advocates. Probably most recently, if you follow the news, you saw our announcement that we have an alliance with ST Micro in Catania, Italy, to be our foundry partner. They don't do foundry, but they're going to be fabricating GaN and silicon for us on 6 and 8 inch lines. And in general, MACOM, is a company with a 60-year history in the RF and microwave business. And just recently, we were reorganized so that I'm responsible for all of our power from the base stations to 5G front-end modules to RF energy, as Pat mentioned, and then multi-market aerospace and defense, L-band, S-band, radar, C-band primarily, but all of those with GaN on silicon technology.
Good afternoon, everyone. I'm Tom Gao from the next local GaN supplier in Suzhou. I take charge in marketing and sales department. The next is dedicated in GaN supplier, IDM model supplier from EPI, wafer, die, and packaging device. We have a reliability test system in-house and provide DC to 6 gigahertz device, power level up to 10 to 300 watt. Okay, and we focus on the wireless infrastructure and we have built a 4-inch product line and mimic design. We cooperate with mainly local customers. Okay.
All right. My name is David Shai. I'm representing Qorvo of USA. So I'm a design manager responsible for 5G mass MIMO and small cell, especially for high efficiency application. Also have some wideband discrete, so under my leadership. So today I'm really fortunately I have been invited here to share our progress, and hopefully we can discuss more about the GaN for the future direction. So Qorvo, we have various GaN from the 0.5 micron all the way down to very, very small geometry. So 0.25, you guys probably already saw a last 0.25 micron right now for the foundry service. We've done even lower 0.13 and even 19 nanometer and also smaller. So we can from from very low frequency up to the millimeter wave range for the GaN. All right, so that's so laid out. So hopefully we can discuss in more detail.
I'm Mark Rocky. I'm representing OMIC. We have been in this business since 1972. This is quite a long time. We are today the only GaN on silicon foundry offering 160 nanometer on silicon, and we have a 6-inch line, which is also unique. And I can tell you, for the first time in 50 years, we are better than Qorvo. We're better than the US. which is, for European, we are extremely proud of.
Okay, so the primary market that everybody's really going after initially is wireless infrastructure. So my next question is, has GaN finally overtaken LDMOS on a performance for wireless infrastructure? Anybody can jump in whenever you want.
Okay, so because in my career, I've been working in this industry for the past 27 years. I have experience with both LDMOS and GaN. So definitely, we are seeing in terms of from education point of view, for wideband application, definitely, so most people renew. So the GaN have a very low output capacitance, so we can, and also a very high power density. So that one is leading in terms of compared to LDMOS performance. And the LDMOS, the probably right now still they are continuing improving. So toward these 3.5 gigahertz, we are seeing in terms of high power range, also higher than 3.5 gigahertz, probably that mainly will be GaN. Okay.
My opinion, I think about 6 gigahertz or 3.5 gigahertz what fixed generation wide enclosure the frequency. Again, it's useful for the power, for the wideband operation and the high frequency and the power density. Yes. So I think if 5 generation, fixed generation comes, again is the most useful semiconductor technology for wireless infrastructure.
Just one word here. I mean, I think you're going to jump on that, but never forget cost. Because LDMOS is low cost. So that's...
Yeah. That one I will debate here.
So are you able to compete on cost?
Yes, certainly. So we all know that again, in terms of power density, probably you can see vary from 5 watt to 10 watt. So probably for most applications, we are able to achieve that, even up to 5-6 years, no issue. So if you compare to LDMOS right now, probably 1 watt, probably the best, probably 1.5 watt. So that's it. So that means the die size in terms of same power level. So you will require much less using GaN, right? So then, of course, then silicon wafer size, which is LDMOS 8-inch wafer, right? So we are approaching to 6-inch. Probably most of the guys probably already have 6-inch, same as us. So we have the 6-inch. We did the cost analysis. So certainly, in terms of from performance and the cost trade-off point of view, so GaN have a big advantage in the future. Okay.
So everybody's a good straight man for us because we've been really focused on that cost aspect as well. Again, with the silicon substrate running at 6 and eventually 8-inch wafers, which I talked about in the intro. So that definitely gives you that advantage and the GaN performance and the power density somewhat in the same range as what you're talking about. We probably don't push it to towards 10 watts per square millimeter just from a reliability standpoint. I think we all optimize kind of what we put into the market based on reliability. But certainly, to echo the comments as well, as we see 5G emerging and frequencies at 3.5 gig, 4.9, we've certainly seen the wireless infrastructure companies come to us for GaN for all of its known advantages, but they want that cost, and they're definitely used to LDMOS. And of course, Pat, I think you know from a SAM standpoint, for at least the existing 4G, the GaN penetration into, let's call it a $900 million market roughly in wireless infrastructure. GaN probably has maybe 200 million of that from at least what I know. So we haven't taken over the 4G piece, but for 5G, I think you'll see GaN take more than its fair share.
Great, and I want to get into right into the GaN on silicon versus GaN on silicon carbide. You know, has GaN on silicon really established itself as a reliable product that can be, offered into the market to compete with silicon carbide?
Okay, we are fully complementary with MACOM.
Your bookending.
So we can be friends here. I mean, it's clear that to achieve. Okay, let's first start saying that Nitronics did a very good job in the early days. And to achieve a reliable, stable gallium nitride on silicon solution processes is extremely difficult. We achieved that. We have proven that, and effectively, the proof of the cake is in the eating. So I mean, it's only the customers to tell that, but it's very easy for me to claim that it's true. But in the talk, I have a presentation right after this one, this panel, and I will go into the details. But it's proven, and it's a combination of two things: of controlling the buffers, which is and the losses in the material, up to very high temperature, because of, you know, the channel temperature can be very high in these components. And second, controlling the surface scraps and steps. So the combination of the two, if you challenge that, if you can achieve that, then GaN on silicon can be extremely competitive. In terms of performance, we see no difference with GaN on silicon carbide, but the cost again is lower.
So just to add a little bit to that, about a year ago, I presented a chart at CS International where I think I took a public survey of 29 or 30 released or available or published GaN processes and showed an Arrhenius curve and where we fit. And thanks for the kudos to Nitronics, but at MACOM we've taken the Nitronics process and improved it. If we call that Gen 0, we're a couple of generations beyond that. We've definitely increased the reliability, we've increased the channel temperature, and the data that I presented showed us in the, let's say, the top 35% in terms of the curves for all GaN processes I could find. So at least in my mind, we've shown that it's just as reliable as silicon carbide processes and other GaN on silicon processes as well.
Okay, it's always at the end is cost and performance trade-off. So we all knew silicon is not as thermal conductive compared to silicon carbide. So silicon carbide is perfect, almost like a perfect conductor. So in terms of thermal wise. So that means when you design it, you will need to have a larger die size compared to silicon, GaN on silicon compared to GaN on silicon carbide. So first, because thermal, so you need a spread in the die a little bit more. Second, the power density, GaN on silicon is lower, so that means you need even larger die size. So overall cost at the end is always performance and the cost trade-off. So you will make that determination, not me. So I'm the design engineering. So we basically will be at the end, we make that decision. We can access GaN on silicon foundry, no issue at all. And we can design our own epi too. So at the end, so who's going to win? And that is really depend on the designer like yourself. Okay?
I'm a designer too, so I don't fully agree with what you said. There's one thing, there are passives, there are combiners, there are vials, there are many other things that dictate the size of the chip. Okay? So you're right, the transistor is one thing, but it's not only that. Okay? So if you have the right values and the right size, you can really minimize the chip size also. Second, when you say you have everything in-house, I know Corvo very well, I don't trust you. The knowledge that is required on EPI is something you cannot buy just overnight. Okay, we have invented the extron reactor in 1986. At that time, VICO was not what it is today. And I think that to have the full EPI capability in-house is essential, and there are very few having that today.
So we're always talking about price performance. I think for price, I think silicon-based GaN will be the best choice, especially for ISM, RF energy, and industry, medical, something like that. And for performance, I think silicon carbon-based GaN will be better, especially for high wideband efficiency, high linearity, So if price performance, customer will be trade-off which the best technology for to adopt. Okay.
Yeah, while it's true that we probably do spread our die maybe more than I would for carbide, and MACOM has some knowledge here because a lot of people in the room know we started with both. Actually, we offered carbide and GaN on silicon. And I mentioned CS International. I actually had a very lively discussion with John Palmer of Cree Wolfspeed last year about this topic. And I think in the end we agreed to disagree, but I think if you look at the cost delta for us to produce on a 6 or 8 inch line versus the slight die size increase, I think we still come out ahead for GaN on silicon as a choice. And we're very, very near carbide performance, whether we're talking about RF energy, wireless infrastructure, or even traditional pulse power radar applications. But in the end, I think I agree as well. Customers choose, and sometimes it's not only those axes. Customers tell us, for instance, that they find our GaN offerings easier to integrate with their DVD algorithms for wireless infrastructure, and I think that's largely due to differences in the trapping effects. But that's their inputs to us. It's not us saying that, but that's what we hear back from them when they use our parts. So those things do matter to the customers, and in the end, I think the panel's right. The customer chooses what best fits.
So I will talk about more in terms of circuit product design point of view. So we know GaN silicon carbide have much higher power density. So your output capacity is much less. So now 5G, we talk about 200 megahertz in continuous bands, or probably minimum 100 megahertz. So now 200 megahertz. So in the future, you never know. So in terms of a wideband application, then if you have a dual band or you have multiple bands, so in terms of those kind of require very high PSAT application. So you may want to choose GaN on silicon carbide instead, for the reason I just described. Right? Number one, power density. The other one, silicon carbide thermally is like a perfect conductor. So several things depend on your application. So certainly GaN on silicon have some applications maybe more suitable for that. But for the future 5G, we're still thinking silicon carbide will be the main track. You can choose silicon, GaN on silicon, certainly for certain reason, so you can use that. However, in terms of cost, you can do a more accurate calculation in terms of later on final your PA pallet size, total size, your material cost. You can make a choice. You maybe need a 2 transistor versus 1 transistor if you're using GaN on silicon carbide versus silicon GaN on silicon. So it really depends. So those applications is really dependent. But I do believe both have their market, right?
Okay, we'll move on to another question. Is GaN challenging GaAs and silicon at millimeter wave frequencies?
So I think I have to talk here. You know, those who have been here around for, like me, for 50, almost for more than 40 years, 45 years, they have known gas MOSFETs, they have known gas PMs, they have known all these generations. And it's very strange. And when RFMD started with the gas HBTs, for example, people have some problem understanding that a technology generation is always going to die and being replaced by a new one. That's life. We have proven, because now we're always talking of GaN as a power technology, but it's also a low noise technology. And we have to thank HRL for that, by the way, because HRL did a very good job. And the situation is that gas, I do believe gas will be dead within a few years, because GaN can replace gas totally. Everything is better.
Including cost?
Including cost, of course, because we're on silicon. So of course. So including cost, including everything. So for me, it's a done thing. Sorry.
And we also have to compare that to RF SOI.
No. I'm talking of application up to 150 gigahertz. No, if you're talking of RF-SOI, I mean, there's a lot of limitations. I mean, that's another story.
I think it really depends on your application and the power level. Like a no-noise amplifier, GaN can do very, very high power no-noise amplifier, but do you need it? Right. So for what application? So may need using GaN instead of silicon germanium or gas or PN. So really depends. In terms of RF-SOI, so RF-SOI is really depends. So in terms of cost, that certainly is pretty low. Right? Silicon germanium also pretty low. So we are not competing in that area in terms of cost for millimeter wave. So the GaN wise, you have the gate length, so it can down to 30 nanometer, so you can do hundreds gigabit. So does that have application using GaN on silicon carbide? Yes, right. So certainly, does a GaN on silicon can do 100 gigahertz? Maybe, but I'm not seeing it.
Please come to me.
Yeah. So I mean, in terms of no noise amplifier, high power, no noise amplifier application, no noise figure, right? So everything has the noise figure. So what kind of noise figure it does require? So PN probably still the best, right? So in terms of noise figure, silicon maybe still catching up in terms of noise figure. But however, so we may agree or may disagree, but that's the majority right on the application for PN, a large no noise amplifier.
Okay, I think what application, depends on what application you need and what performance you need. GaN, if you choose GaN, you may need high frequency and high big power. If you need, I think, for low noise, LNA, I think GaN and gas or silicon germanium, the performance will be similar, just similar. But if you need high input power level, I think GaN will be much better than gas or other technology. For example, GaN can handle 10 times the power level, P1 dB in LNA, low noise amplifier applications, but gas or silicon germanium or silicon will be hard to handle high power level.
Yeah, and you get the advantage depending on the application. If you're in, let's say, a military or radar or someplace where you typically would have a limiter function behind the LNA, with GaN, you can potentially eliminate, and in many cases people have eliminated it. So there's other savings you can get, again, depending on the application that you're in, that comes with choosing GaN over one of the other technologies, even where there might be equivalency in the frequency range. So there are other reasons, and again, we go back to this comment that the user ends up choosing because of their application and the benefits.
Well, that brings up a good point we've talked about LNAs and power.
I just want to add
Go ahead.
First of all, I mean, there's a lot of bullshit about 5G. 5G is high frequencies, millimeter wave. 3.5 gigahertz is 4.5G, it's not 5. Okay? So it's a marketing issue, but it's not real. 5G, beamforming antennas, it's 26 to 40 gigahertz. At this frequency, you need an integrated solution. Even if gas is as good as GaN and noise, that's true, but you want only one chip. You don't want an LNA in gas, and you want a power amplifier and a switch with a different technology. If you can have it in one, then it's much better. And I will go even further, because then we will not be here because we are too old, but maybe one day we will be able to combine that with silicon, one day, because it's silicon. And silicon carbide will never do that. But okay, I'm dreaming.
There's a lot of work on heterogeneous integration, right? So it'll get there. So can we, you talked about LNAs and power amps. What are the advantages for GaN for mixers and switches? Because that's not really discussed a lot.
It's the same thing, it's a dynamic range. I mean, breakdown is always useful, I mean, for any of these applications.
Yeah, in terms of application, like switches application, we know GaN will require negative voltage to switch on and off, and very, very high voltage. So that probably to certain applications is a disadvantage. But in terms of isolation, the GaN can be very, very high. And in terms of the harmonic can be very, very low. So that's the advantage. But however, so that's the switches. So in terms of, so what's the next?
Mixers.
Mixers.
It's like mixer, I'm not a mixer expert, so I won't comment on that, but that's I think the switches application certainly, several occasions already start to use it because like now at a high power level, like you talk about buying a 10-watt switches, which is a mechanical switch or a lot of weight, so it's very heavy. If you're using switches to GaN switches, which is a semiconductor, that's like very lightweight, can handle very high power. So that's an advantage for switches if you're using GaN. Okay.
Yeah, I think a lot of people have in the past said things like, yes, you have high linearity for mixers, but it comes at a cost of a higher LO drive. But I think people have done a lot of work with maybe clever applications of 2-terminal and 3-terminal devices to build a mixer and found ways to get that LO power back down to where it actually makes a very good. So it's kind of the case of people take the available technology and they figure out creative ways to use it and get it to do the things they need to do, and then realize what the intrinsic capabilities are of that technology. So I've seen actually in the mixing space people kind of evolve from, maybe people like Markey in the industry who are well known for mixers saying it comes at a price of very high LO drive, and then other people who have come back and said, no, I figured out how to take that away and created some interesting figures of merit like LO to IP3 and things like that that you can use to measure sort of that metric. So there's actually been a fair amount of work on GaN mixers recently, and I think people are realizing that they can use it quite successfully.
So I maybe add one more. So if right now you are in the market looking for 100-watt switches, so Qorvo have.
Okay, I'd like to open it up to the audience. If you guys have any questions, I can bring the mic over to you and you can ask any of the experts, or if you want to focus on one.
You skipped your last question.
I'm not done. I'll get to that. We have time before your session. Anybody want to ask a question?
That's it.
I have a question. We know that 5G will need a phase shift array, so it will contain thousands, at least hundreds of the front-end module. So I think the cost is a very important factor. So I know that at millimeter wave frequency, integration is very important. So for performance perspective, so we want to integrate everything, for example, in GaN, but I think this will increase a lot of the cost. How do you think that, for example, we implement only PA in GaN, but I only in SOI and other technology? What's your opinion?
Okay, at Atomic for many years we have developed core chips for beamforming using our ED process in PM. We are developing the same thing in GaN, but okay, that will be for limited market. It's true that for the 5G, you will have a TR chip that is GaN, and you will have a phase shifter or a core chip that is silicon. And for the time being, you will not integrate both. That's for cost reasons.
So for 5G, we'll know for the mass MIMO, so like 8x8, so maybe 4x8. So those kind of array, so require a large transceiver, a large power amplifier, and a no noise amplifier. So one thing to reduce cost is integration. So you want to have more integration. So it's not just for millimeter wave. also for sub-6 GHz application. So more integration, that's definitely number one. So number two is how to reduce the overall material cost. Right? So material cost, that's probably the treatment right now from the semiconductor supplier like Volvo. So how we can reduce the material cost? The first 4-inch to 6-inch wafer, right? And also how to increase the power density, so we can use less heat. And we're going to be using the more integration using other technology for integration. So we don't need using GaN. So a lot of low power like a driver, you don't need GaN, right? A lot of passive, you don't need GaN. So like you can use in IPD, you can use in other things. So it's not always about GaN on silicon or GaN on silicon carbide. So for 5G, how we can reduce the overall system cost. So a lot of things, not just from the semiconductor supplier point of view, also from architecture point of view. So you want to choose 3.5 gigahertz, or you want to choose 4.5 gigahertz, or you want to choose millimeter. And we say millimeter wave have their application, but however, millimeter wave cannot penetrate the wall, right? The indoor can be an issue. Maybe you need to install another repeater or other things. So all kind of applications, so either work from the vendor, all the way semiconductor vendor, material vendor, to the service provider, to the systems supplier, so a lot of things.
For massive MIMO application, I think we always need trade-off and the performance and the price. From market feedback, from customer feedback, the module, the 50 ohm match module, the performance, the efficiency, especially the efficiency, not better than discrete solutions. You know, the big guys, they play with the discrete, with Sumitomo, something like that. And for the silicon or GaN module, plastic module, cost is better, but efficiency will be about 5% lower than the discrete solutions.
So Tom used an important word, and I think I'm going to take off my GaN hat for just a minute. He used the word architecture. If we talk about millimeter wave, as Mark calls it, true 5G, and if we treat massive MIMO or multi-user MIMO as 4.5G or on a path through 5G, personally I think they're complementary, but architecture choices are also a way. It doesn't have to be brute force semiconductor integration. And customers have asked us about this, and we've actually made acquisitions where we've acquired some very high-speed ADC and DAC technology. You could envision a system, and I don't want to go into the details here, but you can envision a digital to the element beamforming system. It's a completely different take on how to implement the system, but it provides you a different cost metric as well. So I think, to your question, I think there's going to be a lot of innovation as we see the millimeter wave 5G roll out. And it's a many-year evolution, and I think you'll see interesting architectures at least be tested and then get proven in terms of where they fit on the cost curve.
Okay, great. We have a few more minutes for the one last question. Have Chinese companies established a competitive technology and production capability?
Yeah, I think this is a question for me and for Danex. Danex, I think, is one of the biggest local commercial, I think should say commercial GaN supplier based on IDM model. Okay. We established 10 years ago, and we improved the process and fixed the design a couple years ago, and released a dual pass and single pass device for big guys, and focus on fifth generation projects. We made 8 models. We made high signal models in-house and reliability test system in-house. From EPI to packaging device, we make the whole chain in-house. So it's we have fast feedback time, and we could special design for every strategic customer. So I think this is a local supply advantage, and we have built a good relationship with the big guys, and have strategic cooperation with the big guys. So I think we're ready. We're ready to accept the coming fifth generation network. So this is the next.
Dynex is ready. Okay.
Yeah.
Anybody else have any comments on that?
I probably just have a comment. I think U.S. need to restrict the export restrictions, so that may give China vendor lots of advantage in terms of for high power and high integration type of product. So certainly I think this is my first time joining this conference. I've seen so a few foundry like also Dynex, probably not as foundry, also Sanan as a foundry service for GaN. So look like just based on the discussion, so look like definitely I think it's so beside this export restriction point of view, it's definitely China in terms of GaN development. So which is I think compared just a few years ago, so the performance probably more than a generation difference. Now it's very close. It's closer. But still have several things probably still not as high performance as the U.S. company like over our GaN performance. However, certainly I truly believe in the rising of China in terms of not just GaN or overall wireless infrastructure, wireless communication industry, especially for 5G application.
I'm missing the point here. You mean Chinese people being born in China, or any foreigners coming over to China to install anything? I don't know if you're aware, there's been a revolution in Chengdu. Global, in Silicon there are 4 guys. All the rest is dead. Samsung, Intel, Global Foundries, and TSMC. And Global Foundries is investing billions in a 22 nanometer fab in Chengdu. So this is the end. This is the end. It's no longer China or America. If Qorvo is rich enough, you can have a fab here. Then you don't have any, no problem with Trump or anyone like this. I mean, it's gone. You can do what you want.
Okay, so we definitely have a supply, global supply. So GaN has gone global. So I'll end on that note. Thank everybody for joining us and thank our experts today.
7 billion.